All right, so this is going to be your lesson on types of nuclear reactions. At this point, you should have finished the reading, which was the beginning 2 pages of your note packet. You need to have checked that with me because there are some really, really important concepts in those notes that are in that reading that you need to know. So you got to have that checked. Right now, you need these notes that look like what's on your screen. You need those in front of you, as well as your reference table open to table O. You're also going to be using the periodic table. So the first thing that we're going to start with is natural transmutation. Now, natural means that this is occurring on its own in nature. There's nothing artificial about it. We, as humans, are not doing anything to it. The other thing you might see it called is natural decay. And this should mean something like this. This means something like decomposition. So you want to be looking for something called something that looks like decomposition, which is when you have one reactant and you're going to get multiple products. What happens is an unstable nuclei, and you should know what an unstable nuclei means from the reading. This is when it gives off radiation in order to become more stable. Things in nature want to become stable. They don't want to be unstable. So they give off a type of radiation. The types of radiation are in table O, and this makes them more stable. There's a couple of different kinds of natural transmutation. The first being alpha decay. This is when a nucleus emits an alpha particle. So alpha decay, alpha particle is emitted. An example of this is right below it. But before we get to that example, there's some things that we need to fill in. As a review, this top number, that is your mass number. And that is when you have your protons plus neutrons. The bottom number we should all know, we should all remember, is the atomic number. And we get that from the reference table, which is why sometimes it won't be filled out. So go in your reference table, find RA, and then write down the atomic number. Okay? Do that. I'll give you like 10 seconds. Once you look that up, you should see that it is 88. So you would write 88 there. I'm sorry that's so big, but I can't write any smaller. And then RN is going to be 86. So if you don't know where to find that, please ask me. Now, we should know from conservation of mass, conservation of charge, all that stuff, that everything on this side of the equation has to equal everything on this side of the equation. So since this side is 226, that means that the top of this side has to be 226. So if I have 222 over here, 222 plus 4 equals 226. So that means there has to be a mass number of 4 on this side. And again, the reason why is because 222 plus 4 equals 226. Since I have 86 on this side, and I need to equal 88, that means that there's got to be an atomic number of 2 on this side. Looking in table O, you'll see that 4 and 2 like that is an alpha particle, which we write 4 over 2, but that's not a fraction. He, which is helium, but we also consider that an alpha particle. The other way you might see that is 4, 2, and then an alpha, which that's a terrible alpha, but that is an alpha symbol, which is in your reference table. So that is alpha decay. That is when an alpha particle is emitted. Remember, anything in your products means that it is being emitted, is being released. So that radium is releasing an alpha particle and becoming radon. Okay, so now there's another example here. Write the decay equation for plutonium-239 below. So how we do this is we start with plutonium. So we're going to write Pu. That's what I say in the spring. That wasn't funny. Moving on. Pu, we're going to put 239 as the mass number. And then the atomic number is going to be your, you're going to look it up in the reference table. And once you look that up, you see that Pu is going to be an atomic number of 94. Okay? This is going to yield something plus something. Now, we know that Pu-239 is alpha decay. We know that because it's under the alpha decay part of the notes. The other way you can figure that out is if you flip back to table N. In table N, you find Pu-239 under nuclei, and then go across, and it tells you the decay mode is alpha. That's how you figure this out if it doesn't tell you specifically. So it's alpha decay. So I know that this is going to decay into an alpha particle, but then I need to figure out what else it's decaying into. The way I do that is I take 239 and I subtract 4. That gives me 235. The reason why I did that is because 4 plus 235 is equal to 239, and both sides have to have the same masses. I then take 94 and I subtract 2. That gives me 92. I know that because both atomic numbers have to be equal on both sides. Since that's 92, I then have to find that element in the reference table. So I would go to the periodic table, look up until I find 92, which is on the bottom, and it is uranium. Okay, so that means that plutonium, so Pu-239, alpha decays into uranium-235. Okay, so that is an example of an alpha decay. Beta decay is very similar, except now instead of emitting an alpha particle, we are going to emit a beta particle. And you can see what a beta particle looks like in table O of your reference table. It is a little different than an alpha particle. It has a mass of 0 and a atomic number, an atomic charge -1. So it is a little different. Okay, so doing this example, Pb, you're going to have an atomic number of 82, which you'd find in your reference table. And for bismuth, Bi, you'd have an atomic number of 83. Okay, now notice your masses are the same, and that makes sense because a beta particle doesn't have mass. So your masses are going to be the same, and then the charge of a beta particle is -1. And that also makes sense because 83 minus 1 is equal to 82. So your sides are equal. Both sides always have to be equal. So that is a beta particle. We draw that by writing a little beta symbol. It's basically a capital B with a little tail on it. The other way you could see it is O minus, or 0 minus 1, and then an E, because if you look at it, a beta particle is actually the same thing as an electron. Okay, it's got a 0 charge, or 0 mass, -1 charge. Okay, so it's the same thing as an electron, so you could see it written like that as well. Okay, so now let's do an example of this. Write the decay equation for gold 198. So you know that gold is going to be Au. Its mass number is 198, which you get right there. And then you need to look up its atomic number, which is 79. That comes straight from your reference table. This is going to go through a beta decay. And again, you can always check on whether it's beta decay or not by looking in table N. I'm going to tell you this is beta decay. So that means it's going to have a mass of 0 and a charge of -1 for your beta particle. So then to make sure that these are equal, you have 198 on the top, and you have 80 on the bottom. Why that's 80 is because you do 80 minus 1 is equal to 79. So now I have to figure out what a mass number of 80 is, and once you look that up in your reference table, you would see that it is Hg, or mercury. So that would be your completed decay equation there. Positron decay is, again, similar to alpha and beta, and I bet you can even guess what it emits. It's a nucleus that emits a positron. Positron is something that we have not heard of before. It is, again, in reference table O if you want to take a look at it to see what it is. And it's the opposite of a electron is when you have a 0 mass but a +1 charge. That is not a proton, though, remember, because a proton would have a mass. A positron is basically just a positive electron. And we can, the symbol for it is O over +1 E, or 0 +1 with a beta there. So again, it looks very, very similar to beta decay, except instead of -1, it's +1. So neon goes through a positron decay. You look up the atomic number, it's 10. Look up the atomic number of fluorine, it's 9. Okay, so now we have a mass of 0, which makes sense because our masses are equal. But here I have 9, so that means this has to be +1 is equal to 10. So that's going to be 0 over +1 beta. And again, to do an example of this, we have Ca37. The atomic number is 20. And this is going to go through positron decay. So that's 0 +1 beta symbol. And then that's going to be the same mass, because again, this is 0. And then now I need to take 20 and subtract 1, so that would give me 19. And an atomic number of 19 is potassium. Gamma radiation. Gamma radiation is, you've probably heard of it before. It is how Bruce Banner turned into the Hulk because he was doing some experiments with gamma radiation, and he turned into the Hulk. Gamma radiation is also what they find coming off the Tesseract in the first Avengers, and yes, all my examples of gamma radiation come from comic books. Gamma radiation, there is no change in mass or charge, but a large difference in energy. So large difference in energy. That makes sense because your symbol for gamma radiation is 0, 0, then with that gamma symbol, which I don't draw well, but that's a gamma symbol. So that means no change in mass, no change in charge, but gamma radiation has extremely large energy. Gamma radiation is extremely dangerous too. It's the highest penetrating power of anything. It's very dangerous. You don't want gamma radiation going through you. I can tell you that if you get hit with some gamma radiation, you do not change into the Hulk. It's no bueno, no bueno. Now we're going to move on to artificial transmutation. Artificial transmutation is when we do something to it. So we have a stable nucleus, but we don't want it to be stable, so we make it unstable by bombarding it with radiation or particles. Basically what we do is we fire radiation or particles at it so that it becomes unstable, and then it releases stuff and it becomes something else because it was unstable. So this is artificial transmutation. So we look at this, and this is an example of it. We have nitrogen 14. We know the atomic number of nitrogen is 7. So we put that in there. We know the atomic number of oxygen is 8. And we know the atomic number of hydrogen is 1. So if we do 17 plus 1, we get 18. So that's what the mass must equal on the left side. We get 8 plus 1, we get 9. So that must be what the atomic charge must equal on the left side. So since I have 14 right here, that means 14 plus what must equal 18? Well, that's got to be 4. Now I have 7 on the bottom. I need to make 9, so that's got to be 2. So this is telling me that in order to make nitrogen 14 unstable, we bombarded it with an alpha particle. So we bombarded it with alpha particles. So we added an alpha particle to nitrogen 14. That made it unstable so that it transmutated into oxygen 17 and a proton. So this is also a proton. It released a proton along with this. So that is artificial transmutation. Now, fission is a type of artificial transmutation that we will get to later. So those are your notes for types of reactions. Now, what you need to make sure you do next is go to this worksheet, complete this worksheet, and then show it to me, and then you're done with radioactive decay, and you can move on to the next one, which is fission and fusion. If you have any questions, please let me know. If anything didn't make sense, please let me know. Other than that, do this practice worksheet, check it with me, and then you can move on to fission and fusion. Thanks.